All right, today is May the 4th. That would be Star Wars Day. And therefore, we're going to talk about power, like the power of the Force. No, well, not quite, but we are going to talk about power of electrical circuits, which is almost as exciting. So, we're going to start with our basic definition of power that we already know. We already know that power is energy over time, and that energy is related to work. And so we're going to start with this definition right here. Power equals work over time. Now, we've talked about electrical charges already, and we've talked about how work is related to electrical charges by the electrical charge, Q, multiplied by the potential difference of the path that it's taken. And so if that's the work, then we can follow over here to say that power is the charge of the particle times the change in potential, or the potential difference, divided by the time. Now, you would notice here that Q over T, of course, is current. And so if we take Q over T and turn it into current, we get our final equation right here, which is P equals IV. Now, you need to recognize that this is the equation that will be given to you on most exams. You will not be given either of these two up above, but of course they can be used if you can do the derivation so that it works. Now, what I'd like to go over next is just how we can use I, V, and R so that we have power in different forms. Now, these are actually all given to you on your IB exam booklet, but I just want to make sure that you know where they're coming from. All right, so the first one that we're going to do is, well, we know, for example, that V equals IR. So if I do V equals IR, and I put that in for V, then I would get P equals I, IR, right? Instead of V, I've got IR. And so then I would have P equals I squared R. And so if I have current and resistance, I can get power that way as well. Now, of course, I could do it the other way. I could just as easily say, well, we're going to solve for I. And so if I solve for I will have that I equals V over R. And so if I do that, I can put V over R in for I, and then I would have V squared over R. So I can also have that power equals V squared over R. All right, so I've got three different equations, P equals IV, P equals I squared R, and P equals V squared over R. Now remember that this is the power it could be the power lost in a resistor, the dissipated power. It could be the power being generated by a cell or a battery, right? And so it would be whatever the current was for that object, whether it be the battery or the cell or the resistor, the potential difference across that object, and the resistance through that object. Okay, so hopefully that'll be helpful as we go through a couple other things. Mostly this is going to be used with resistors or things that are similar to resistors. All right, so now we go into a resistor of resistance 12 ohms has a current of 2 amps flowing through it. How much energy is dissipated in the resistor in 1 minute? All right, well, it says energy dissipated in 1 minute. So that's energy in time. So that should clue off that I'm looking for power here. So if I look at power, I'm given resistance in ohms, and I'm given current. So the equation that related those two was power equals current squared times resistance. And so with that, I should now be able to calculate. And so I'll go power equals, and so I was 2, so 2 squared times the resistance, which was 12, and so that would be 4 times 12. The power is therefore equal to 48 watts. Now, of course, that is watts, which is joules per second. So since that is joules per second, I need to figure out in 1 minute. So I'm going to multiply by 60 seconds per minute. And if I do that, 48 times 60, that should give me my final answer. And so that gives me that the power is 2880 watts per minute. How much energy? Or sorry, not watts per minute. That would be joules per minute because there's joules per second. Now, in keeping consistent with IB, since this has 2 sig figs and this has 2 sig figs, my final answer should also. So you can either say power equals 2,900, or we can just say equals 2.9 kilojoules. All right, let's move on to the next one. Okay, so now I've got a light bulb that's rated at 60 watts at 220 volts. Across that light bulb, I add a potential difference of 110 volts. Okay, now this is important that it's rated at 60 watts. So what that means, now you'll remember from our experimentation in class, we had a light bulb, right? Something like this, and you had to put one wire here and one wire on the tip there at the bottom, and that potential difference is what caused the current to flow in through the battery and then out, which then caused the light bulb to light up. So if I have 220 volts here, then the power out will be 60 watts. Now, what it's saying is I don't have 220 volts, I have 110 volts. So how much power is going to come out? Okay, well, the first thing we have to recognize is that the volts is changing, all right? The volts is changing, so the power is going to have to change. Now, if the volt changes, potential difference changes, then the current's going to change. Now, the one thing that's not going to change is something that depends on the physicalness of your system here, which is the light bulb, and that's the resistance. The resistance of your filament, of your light bulb as a whole, is not going to change. So what we're going to do is we're going to use the power and potential that have been given to us to find a resistance. Now, that would be power. Sorry, my pen isn't working. Power equals voltage squared over R. And so I'm going to go ahead and put in the power that was given to me, the 60 equals the voltage squared, which is 220 squared over R, and I'll calculate the resistance. So I'll take 220 and then square it, and then I'll divide that by 60, and that will give me 2,420 over 3. So resistance equals 2,420 over 3. All right, so now that I have the resistance, I can put that in with the given potential to find out what the new power will be. All right, so let's go ahead and use the equation again. So this time we'll say power equals, but this time I've only got 110 watts. Now you can probably figure out that there's an easier way to do this, but we'll go ahead and do it this way first. So 2, 4, my pen's decided it doesn't want to write anymore. 2, 0 divided by 3. All right, so I'll go 110 squared divided by 2,420 over 3. And when I put that into my calculator, I will get a power rating of 15 watts. Now, that should make sense, and like I said, there was an easier way that we actually could have worked through that, because we could have just said, okay, well, if power equals voltage or potential over resistance, if the potential is halved, which is what happens when I go from 220 to 110, the potential is half, that's going to be squared, which means the result is going to be 1/4 of what it was before. And so if it's 1/4 due to this squared relationship, then it'll be 1/4 of the power. 1/4 of 60 is 15. All right, so that's all for this video. Why don't you go on to the next one and look a little bit at some resistors. All right, so what we're going to do is we're just going to do some simple calculations here dealing with resistance. All right, so I've got two sets of resistors here. First, we're just going to kind of get used to the idea of the resistors, and then we'll look at some actual circuits and deal with it as best we can. All right, so we talked about in class the difference between parallel and series resistors, and we talked about how if it's in series, if it's one right after the other, then we're able to just add the resistances together. If the current has to split, then we have to use the 1/R plus 1/R equals 1 over the total. All right, so in this case, what I'm going to do first is we're going to go ahead and find the effective resistance of these two together. All right, and so what we're going to do is we're just going to go 1/4 plus 1/8 equals 1 over the total resistance. Now that total resistance is just this red part here. So if I find a common denominator, that will be 2/8 plus 1/8, that is a plus there, equals 1/RT. So that would be 3/8 equals 1/RT. Now, you'll notice that that's just the reciprocal. So that means that the total resistance there is the reciprocal of 3/8, which is 8/3. So 8/3 ohms. All right. Now, we'll notice also that this resistance here is less than either one of those resistors was in the beginning. That's an interesting phenomena that we can take resistors, and if we put them in parallel, then we end up with a resistance that's less than what we started with. And that's because the current is having to split up here as it goes through those resistors. And so you're getting less potential drop. And so sorry, not less potential drop, but you're losing less power over each of those resistors because of the smaller current. And so it's important to recognize that, yes, the total resistance there will be less. Now that I'm in series, because essentially if I do this and these two together now give me a single resistor of 8/3 ohms, same thing, then I can just add these two together. So the 2 ohms would be 6/3, so that would be a total of 14/3 ohms. Okay, not so bad. Let's go on and look at the next one, which is very similar. It's just adding in a little bit more. So this one, I have 4, which are all 1.5. Okay, 1.5, 1.5, 1.5, and 1.5. All right, so again, I see that if I could just go straight through here, then they'd be in series, but I've got these two that are in parallel. So I'll go ahead and take the 1.5s. Now, you could do 1/1.5 plus 1/1.5. I'm actually going to simplify this because 1.5 is 3/2. So the reciprocal of that is actually 2/3. And so if I go 1/3 plus 1/3 equals 1 over the total resistance, then that's just the same thing as 2/3 plus 2/3. Now, you could do the 1.5 and it's fine. You'd get the right answer. But sometimes the fractions are easier to work with. And so now I'll get 4/3 because I add the fractions together, which means that the total resistance equals 3/4. The reciprocal of that, right? All right, so I've got 3 over 4, so that means that these two together now are 3 over 4 ohms. Now, the second set, of course, is exactly the same, so that will be another 3 over 4 ohms. And if I add them together, because they're in series now, 3/4 and 3/4 is a total of 1.5 ohms. Okay, and you may think that's kind of weird that I can take 4 1.5 ohms resistors and put them together and end up with a resistance that's still 1.5. But and you may further ask, why in the world would I want to do that? Well, I'll tell you why you might want to do that. You might have something that needs a smaller current, right? And so you could connect something here that goes through that then could use a smaller current. Okay, you could have something that needs a smaller resistance, in which case just part of this, 3/4, would be, a smaller resistance than the 1.5. And so this is a way, using your resistors in a creative way, gives you ways that you can split the current in different ways. It gives you ways that you can get the voltage to do different things. You can get, obviously, resistance to be smaller if necessary. And so you can do a whole bunch of different things if you are creative with how you organize your resistances. All right? So just be aware of that. All right, well, that's the end of this video. If you want to go on to the next one, we'll actually start looking at some circuits. All right, so we are going to calculate the currents in this circuit right here. Okay, just with the information that we already know. All right, so we're going to just start right away. Now, the first thing we're going to do is we're going to take, we know, let me just remind you that we know that V equals IR. Okay, now this is significant because I can use V equals IR. I can use V equals IR for a whole circuit, and I can also use it for an individual resistor. Okay, and so what I want to do, if I want to be able to find, for example, I1 is the current going through the whole circuit, right? It actually gets split up here, gets split up right here for when I go into I2 and I3, but then it comes back. All of the current has to go through all of this wire right here. There's nowhere else it can go. If we are conserving charge and conserving energy, it's got to go through there, right, until it gets here and splits up. So if I can find the total resistance of the circuit, then I can take the total potential of the circuit and I can calculate the total current, or the maximum current in the wire right there. Okay, so that's the first thing that I'm going to do. I'm going to calculate the total resistance of the circuit. So in order to do that, I'm going to try to put these two together. So I'm going to go 1 over 6 plus 1 over 9 equals 1 over the total resistance. All right, common denominator probably 18, so 3 over 18 plus 2 over 18 equals 5 over 18, which means that the total resistance right there equals 18 over 5. So I could combine those two, and they now become 18 over 5. Now, now that it's all in series, I combine those two to become the 18.5. So now that it's in series, I can now add the 3.0 and the 18 over 5. Now, 3.0 is 15 over 5. And so I add those together, I get 33 over 5 for the whole resistance of the whole circuit. So resistance equals 33 over 5. I know that the potential for the whole circuit is 3.0 volts. And so I can now calculate the current, because I can go V equals IR. So V is 3. The current is current 1, I1. That's what I'm looking for. And the resistance of the whole circuit being 33 over 5. And if I multiply both sides by 5 over 33, then I will get that I1 equals 5 over 11. So that 5 over 11 amps is the current for I1. All right? Now, I need to figure out at this point, so I'm going to get rid of some of this stuff that I've written on here, hopefully. There we go. I now need to figure out I2 and I3. Now, in order to do that, knowing that V equals IR, knowing that I have the resistance, what I need here is I need the potential that's lost over this segment right here. Now, I know that the total circuit has 3 volts. What I can do, now that I have the current being 5 over 11, is I can find out how much potential is lost here. Whatever's lost here, the leftover then has to be lost in the parallel circuit here, which means I have to lose that much on the top and on the bottom, because the potential has to be the same. The potential difference has to be the same on the top and the bottom. All right, so I'm going to go ahead and find how much is lost here by doing V equals IR. So V is what I'm looking for. I know the current through the 3 ohm resistor because the current was 5 over 11. And then R, of course, is 3. So the voltage there is 15 over 11. So the potential difference lost here is 15 over 11. 3 volts would be 33 over 11. So 33 over 11 minus 15 over 11 means that here I'm losing 18 over 11 volts from this point to that point. All right? So both of these resistors have to have a potential difference of 18 over 11. That means I can solve both of them fairly easily now, because now I can do the 9 ohm resistor, and I can say that the potential difference, 18 over 11, is equal to V equals IR. You can see I'm using the same formulas over and over and over again. The current, I2, is what I'm looking for. The resistance there would be 9. So I divide by 9, and I get 2 over 11 is I2. That wasn't too bad. Then I can do the same thing for I3, because I3 also has to have a potential difference of 18 over 11. So that will be I3 times 6 ohms divided by the 6, and I'll have 3 over 11 equals I3. Now, I mentioned the conservation of charge earlier. That means that I1 here is going to split into 2 and 3. So whatever current is coming through here has to be total in those two. You'll notice that I2 right here is 2 over 11. I3 is 3 over 11. If I add those two together, I get 5 over 11, which is the current in the whole thing. All right, let's go on. Let's look at another one. Okay, see if we can get comfortable with another kind of question. So here we've got the current in a 2 ohm resistor when the switch is open and when the switch is closed. So it's asking us to find the current in the 2 ohm resistor, this one right here. Oops, yep, that's what I meant. This one right here. I'm looking for the current there when the switch is open and then also when the switch is closed. Here's the switch. You can see the switch right here, it's S. So right now it's open, which means there won't be any current flowing here. When I close it, the current will just flow straight through, okay? And then potential difference across the 2 marked points, A and B. So what's the potential across here? All right, now I'm actually going to talk really quick about what happens when the switch is closed first, all right? Because that's going to be the easier thing. So if I close this, that means you see the battery down here, okay? The battery, the long end is always the positive, the short end is the negative. So that means my current's flowing this way, okay? So if my current's flowing this way and it gets up to A, it looks almost like I have a choice of which way to go. And the current technically does have a choice. But if we're assuming that our wires have no resistance, that they're perfect wires, then the current is not going to go up here and fight through that 2 ohms of resistance. It's going to say, well, would I rather go through 2 ohms of resistance or would I rather go through no resistance? Well, it's always going to go through the no resistance. Okay? If it has a choice between 2 and 4, then some of it will go through the 2, some of it will go through the 4, because you have to have a potential difference across both of them. But here, because there's a wire and because there's no resistance here, if there's no resistance, then there can't be a potential difference. And so therefore, to answer the question about when the switch is closed, what's the potential across A and B? Well, the potential there is 0. The potential difference there is 0 because there's no resistance. And if there's no resistance, all the current is going to go through there. So that answers 2 questions. What is the current across this one? Well, the current's not going to go through that one, right? The current will not go through the 2.0 ohms because it's all going to flow from here, and then it'll split to go through the 4 ohm resistors. Okay? So what is the current in the 2 ohm resistor when the switch is closed? Well, the current is 0. And what is the potential difference across the 2 marked points A and B? The potential difference is 0. All right, now let's go into what may be a slightly harder question, which is the other question that was asked. Well, what about when the switch is open? All right, so let's go ahead and start looking at that and see if we can figure out what the answer to that question would be. Okay, so we notice here, I talked about the fact that we had the positive right here, and we had the negative over there. So my current's going to go this way. Now when it gets to A, it's definitely not going to go through S, because that, since it's open, it can't get across. That's essentially an infinite resistance, and so it's going to say, I'm never going that way. And so it's going to go on up to the 2 ohm resistor. It'll go through the 2 ohm resistor. It'll get to this junction. At this point, it's going to choose. It can either go this way or it can go that way. Again, it's not going to go over to the left because of the open switch, so it's going to go here. So essentially, it chooses to go through one 4 ohm resistor or the other one. It's going to meet back up, and then it's going to go back to the cell to finish our 12-volt potential difference. So everything has to go through the 2 ohm resistor. It's going to split here. Because it's splitting, the split here results in a parallel circuit. So the first thing we're going to do is we're going to figure out how much resistance is there in that parallel circuit. So I'm going to go 1 over 4 plus 1 over 4 equals 1 over RT. So then I've got a total of 2 over 4 equals 1 over RT. So RT, the total resistance, equals 2 ohms. Right, 4 over 2, it's the reciprocal. So if I get rid of these and ignore them just for a minute and say, well, all of that is in this resistor right here, essentially it's the same thing as a 2 ohm resistor. All right, so now I've got 2 and 2. That gives me a total of 4 ohms going through the whole circuit there. So the total resistance of the circuit is 4 ohms. The potential difference for the whole circuit is 12 volts. And so then I can do V equals IR. Wow, I use this a lot, don't I? Yep, get used to it. So 12 equals the current times the resistance, divide, and we get a current equal to 3 amps. Okay? Now, the question was, what is the current in the 2 ohm resistor? Well, all of it is going through there. So because it's all going through there, then the current through the 2 ohm resistor is 3 amps. When I get to the 4 ohm resistors, the current's going to have to split, so it'll be less. But at the 2 ohm resistor, it's all going through there. Okay, so the answer to this first part, when the switch is open, the current in the 2 ohm resistor is 3 amps. Now, the next part asks for the potential difference between A and B. So to get that, we need to find out how much potential was lost between the beginning, which is A, which is this part right here, which is all the same. All of that is the same. And then between point B, which is here, and that means all of this is the same. Anything connected by wire and no resistor, all of that should be the same potential. So the potential between A and B is the potential between the blue and the red. The only place I'm losing potential is across that 2 ohm resistor. And so in order to find that, of course, I'm going to use V equals IR. And I know the current because I just found it. The current was 3. And I know R because R is given to me. It's 2 ohms. And so I can calculate V, which is 6 volts. And so the potential across from A to B is 6. And that's the end of that question. Let's go on. Let's do one more. This is fun. This is fun, right? We can do one more. All right. This is another interesting one with something that happens later on. So we've got 4 light bulbs. Each has 60 ohms of resistance. Find the power in each light bulb. So we'll do that first. Find the power in each light bulb. So in order to do that, of course, I'm going to look at the full circuit. In order to look at the full circuit, whole thing, right, starting at the positive right here, going to the negative, so I'm going this way. In order to look at the full circuit, which the full circuit is 30 volts, I need to know the total resistance. If I know the total resistance, I can get the current. Once I know the current, I can figure out the power through each of the bulbs because I can figure out the current through each of the bulbs. All right, so let's start with that. Let's find the total resistance. So here, these two right here are in series. So I'm going to put those together. That'll give me 120 ohms total. It's just like there was one resistor there of 120 ohms. These are bulbs, but bulbs are essentially resistors, fancy resistors that happen to light up. Okay, now I've got these two right here, which are in parallel. So I'm going to go 1 over 60 plus 1 over 120. Okay, which will be 1 over that total resistance. And so I'm going to do 2 over 120 and 1 over 120, so that'll be 3 over 120. 3 over 120 reciprocal would be 120 over 3, so that resistance will be 40. Okay, so all of this together is essentially 40 ohms. 40. All right. And if I add that 40 to the 60 here, that means my whole circuit has a resistance of 100 ohms. Now I'm going to shrink this and give myself a little bit more space to work. So 100 ohms total, 30 volts. So I can go V equals IR. V was 30. I is unknown. R is the total resistance, which we just found out to be 100. Divide by 100. The current in the whole circuit is 0.3 amps. Now, it wants me to find the power for each bulb, right? It says find the power in each light bulb. So that should be easy for the first for this lamp right here, because in this lamp I know the current, which is 0.3 amps, because all the current's got to go through there, and I know the resistance, and so I can use the formula P equals I squared R. And so I do that's a big decimal point, 0.3 squared times 60. And when I work that out, that will be 0.09 times 60, which gives me 5.4. So I'll have a power of 5.4 watts there. Okay, and then I move over to these guys. Now, if my, I guess it would be helpful if I know the voltage drop here, because if I know the voltage drop here, I'll be able to figure out the voltage drop for this other mess of bulbs over here. So I'm going to go ahead and do that while I'm at it. So we'll go back and we'll say V equals IR. And as I'm doing that, the current will be 0.3. The resistance is 60. So I get 18 volts, which is more than half, right? Which makes sense because this was 60 ohms and that whole thing over there was only 40. So most of the potential is being used up here. You can then guess that most of your power is going to be there. That's probably going to be our brightest bulb at 5.4 watts. Okay, so we know that 18 volts is lost there, so that means that 12 volts is lost in this whole system here. 12 is my potential difference. Now, if that's the case, then this bulb right here on the bottom, that one bulb is going to have a potential of 12. So again, I can use power. I can go power equals V squared over R. So I'll go power equals, so this one will be 12 squared over R, which is 60. And so that would be 144 over 60, which is 12 over 5. 12 over 5 is 2.4 watts. Okay, so that would be this guy down here. Now those guys up there, still 12 volts of potential, but there's two of them. Now since the same current's going through them, they have the same resistance, then I can simplify just by saying I'm going to lose 6 volts here, 6 volts there. So I can do the same thing. I can go power equals V squared over R. So that will be 36 over 60, which gives me 0.6. So 0.6 watts, okay, for both of those bulbs. So I've got 2.4 down here. Oh, I didn't need to change that color. So 2.4 for this bulb right here. This bulb has a power of 5.4, and then those two bulbs at the top have a power of 0.6 watts. Okay, so they're the dimmest. All right, so the next part, we're only halfway done. It then says if light bulb A burns out, find the power in each light bulb and the potential difference across the burned out light bulb. Okay, so in order to do that, we're going to say, okay, well, if bulb A burns out, what's going to happen? So I'm actually going to take my eraser and we're going to erase everything that has here, because you can just rewind your video at any point in time if you need to. So we're going to erase, whatever I can. Whatever I can't, we'll just deal with. Looks like it's not going to let me erase the red. Maybe it's been there too long or something. I don't know, but we're erasing everything else there with my calculator. That's okay. It's Star Wars Day. I'm okay. So here we go. If bulb A burns out, bulb A is now gone. Now, what that means, generally when a light bulb burns out, the filament breaks, right? Which means that you're not going to get any current going through there. Now, if there's no current going through A, then when the current gets here, current's going this way, it's not going to go towards A at all, right? Because it can't get across. And so all the current is going to go down here through C and then back this way. It's not going to go up to B because it doesn't have any reason to, right? All the potential, there's no resistance there. Actually, there's infinite resistance here, which means no current wants to flow that way at all. All the current is going to go through C. So essentially what I have now is that I have C and D, which are in series, right? The parallel isn't going to happen anymore because the current's all going to flow around and it's not going to go through A and B at all. So I can now recalculate everything. We can go V equals IR for the whole circuit. So V equals IR. The potential for the whole circuit is still 30. My battery is still the same. I can calculate my current because the total resistance is 120 ohms. And so now the current will be different. I'm going to go 30 divided by 120. And so now 30 divided by 120, 30 is a quarter of 120, so that would be 0.25. So I actually have less current flowing through, and that should make sense. Because it's not splitting up here, then I'm actually losing less potential than before. Because I'm losing less, well, I guess, sorry, the potential has to be the same, but I'm losing it in less locations. And so the power dissipated is going to be less. So I'm going to have less current going through because I have less light bulbs that are being powered with that potential difference. Okay, so now that I have that, I can actually calculate the potential difference across the burned out light bulb. I also want to look at the power in each of the light bulbs that's remaining. These two light bulbs, of course, A and B, will have no power at all, right? Because there's no current flowing through there. This light bulb, C and D, will both have the same power because they both have a current of 0.25 and they both have a resistance of 60. So we know that P, like I did in the first one, P equals I squared R. So I was 0.25 squared and then times 60. All right, so when I calculate that, then I'll have 0.25 squared times 60, which will give me 3.75. And so now my power will be 3.75 watts. So what you'll notice is that the one that was in parallel, the C over here, it's up to 3.75 watts now. It's actually increased its wattage. It's going to get brighter, okay? The one that was all by itself in series, that one, actually, remember before it was 5.4, now it's down to 3.75, so that one's actually going to get dimmer when A burns out, okay? And that's all a result of what the electricity is doing now and the path it's going to take. Okay, so we now know the power. Those two are 0. This one has the power of 3.75, and then the D also has 3.75 watts. All right, and we've noticed the difference in what happens to those powers based off of where they are. Now, I'm also going to look for the potential difference across the burned out light bulb. So that's the potential difference across A here. Now, the potential difference across A is what's happening here and what's happening over on this side, right? Because nothing's flowing through B. So that's the potential difference I'm looking at. So it has to be whatever the potential difference is across the 60. That same potential difference will take place because no current's flowing. There's no resistance here. And so therefore the potential will be across A. So in order to find that, I'm just going to go V equals IR over here on the right. I will find the potential by taking the current, which should be the same as, sorry, I'm looking at the potential lost across C, because that'll be the same as what's up here because of the parallel circuit. So the current there was 0.25. Actually, I really don't need to calculate this because I already know it's going to be 15. How do I already know it's going to be 15? Well, because the total voltage was 30. And if half of it's being lost here and half of it's being lost there, because it's the same resistance and the same current going through both of them, then it's got to be 15 volts. All right, so that's the end of this question, the end of this video. If you want to see some more, go to the next video. All right, so to finish up today, I want to introduce you to Kirchhoff's laws. Okay, and I'm going to give you some formal definitions, and I'm going to give you some working definitions and things that are going to help to figure things out. All right, so first, Kirchhoff's first law is essentially conservation of charge. In fact, both of these are essentially conservation of charge, conservation of energy. You can't destroy charge. Charge that is there will continue to exist. All right, so this one says the sum of the current into a junction is equal to the sum of the current out of a junction. Okay, so basically, here we go. I got a junction. I've got some current flowing in, I've got some other current flowing in, I've got some current flowing out, and I've got some current flowing out. So this is I1, this is I2, this is I3, this is I4. So basically it's saying whatever comes in to this junction, that wire where they cross, whatever comes in has got to go out somewhere, okay? That's your kind of your formal definition, maybe your layman's definition, whatever goes in must come out. The way that I like to work this mathematically is I like to balance the two sides of the equation. Some textbooks will teach you going in is positive, going out is negative, add it all together to get 0. I find it easier if I just say the current in current 1 plus current 2. Right, because those are both going in, has to equal the current in 3 plus the current in 4. Right? You do that, n equals out, that's it. Okay? Plus, then all of your values can be positive. Your currents are all positive because they're all moving in the direction of the current you've identified. And this just simplifies things a lot down the road, okay? So this is fine. You're more than welcome to use the formal definition, which is that the sum equals 0. If you do that, however, you have to recognize that there's a convention that currents going in are positive, currents going out are negative. All right? So, do what you may. This is what I'll be using in my videos because I think it's the easiest way to interpret it. All right? On to the next law, which is Kirchhoff's second law. Duh, the first one was the first law. So we're on to the second law, which is that the sum of all variations in potential in a closed loop is equal to 0. All right, so maybe I don't understand exactly what that means. Basically, this is the sum of the, how you love spell check. The sum of the EMFs in a closed loop is equal to the sum of the potential differences in the loop. So basically what this is saying is that you're going to have EMF, you're going to have batteries, you're going to have cells that put energy into the loop. That is going to be exactly equal to the IR, right? That's when I'm using the V equals IR, which is generally the resistance that's being lost through a resistor, the current going through the resistor, so it's the potential lost in a resistor. So this is just saying that my gains need to equal my losses, okay? Now, personally, the way I like to work through this is if I'm going through a loop, because I'll show you an example of this. When we go through a loop, if I go through something that causes me to gain potential, then I'll just put it down as a positive potential. Okay, if I go through something that causes me to lose potential, then I'll just say minus potential. Okay, and I'll subtract that. And then if I go through something else that causes me to gain, then I'll just say, okay, plus potential. The reason I like this is because with the summations, you have to have all your summations first on the left-hand side, and then you've got to have all your losses on the right-hand side. What this does is it just allows you to go through the loop, write down one right after the other, go through the process, figure it out, and then at the end, the summation of all that should equal 0. That's kind of this one right here. The sum of all the variations in a closed loop should be 0. I'm using negative for potentials lost and positive for potentials gained. Okay, again, this is just conservation of charge, conservation of energy. It's got to remain constant. You can't lose anything. Okay, let's go on to the next slide and demonstrate this for you. Okay, so here I'm going to calculate the currents in the circuit. Now, you may recognize that we did a question, this exact same question before, and in the previous time we did this, we actually took these, whoa, I didn't mean to do that. We actually took these values right here for the resistors, and we found the effective resistance. We put the resistors together. We used V equals IR, all that fun stuff. What we're going to do now, though, is we're going to talk about a different way to do this by using Kirchhoff's laws. Okay, and you may get to the end of this and be like, well, why in the world would I ever want to use Kirchhoff's laws? That's so confusing. Well, it's the idea when you have a circuit where you can't tell which direction the current's going because there's like 3 batteries that are all facing different directions and resistors and all sorts of other things, this simple idea of just putting resistances together is not going to work very well. Okay, so I'm going to show you how to use Kirchhoff's laws so that you'll be able to apply it in various situations later. All right, let's just go through this first. Okay, so Kirchhoff's laws. I'm going to start with law 2. Okay, law 2 says that if I go through a loop, that the potentials have to add up to 0. The gains and the losses have to even out. Okay, so you see the direction that my potential is going. I've got a positive here. I've got a negative there. My current will go this direction around the loop. So you can see the current directions are already marked. If you don't know the direction, then just label it. Choose a direction. Okay, if you end up getting a negative later, that just means that you chose the wrong direction for your current and you just change it and it goes the other direction. All right, it's not a big deal, but generally speaking, you can figure it out. I can tell because of the battery here, it's going to go through the loop this way. It's going to go through my resistor. When it gets here, it's going to split and go one way or the other. It's going to go through my two resistors, and then it's going to join back together and then come back to the battery. Okay, now for Kirchhoff's second law, I need to choose one loop. No splits, just a loop. So what I'm going to do is just follow the outside loop here, all right? So the outside loop is going to look like this. I'm going to start just on this side of the battery here. Okay, so I'm going to start right there. I'm going to go through the battery. So when I went through the battery, I just gained some potential. So I'm going to go V. Now I actually know what that V is, so I'm not going to put V. I'm going to put 3 volts. Okay, so that's positive because I went the right way through the battery. If you go the wrong way through a battery, that's fine. You just put down that it's negative, that you lose potential going to that side. So I gain 3 volts of potential. Okay, follow the current. Now I'm going to go through a resistor. If I go through a resistor, I'm going to lose potential, right? How much potential? Well, I'm going to lose V equals IR. The current there is I1, and the resistance there is 3. So 3 times I1. Okay, so I go through that resistor. Now I'm following the outside, so I'm going to choose this direction. I'm going to go through here. Now you'll notice I'm going through another resistor in the direction that my current tells me that I'm going. And so I'm going to subtract again. I'm going to go minus 6 ohms is the resistance times I3. Okay, I go through, I join back up, and I go back to the battery, right back to where I started from. I didn't pass through anything else. So that's it. I gained 3 up here. I lost 3I1, and I lost 6I3. All right, all of that, when I put it together, needs to equal 0. That's my first equation. All right, so that's one. Let me show you an example of using Kirchhoff's second law. I'll show you what we're going to do with this. Now, the question, of course, is asking for us to calculate the currents. I should have gone into this initially. I've got 1 current, 2 currents, 2 currents, 3 currents. So I need 3 variables. That means I'm going to need 3 equations. So I got my first equation from Kirchhoff's second law right there. So I'm going to use Kirchhoff's first law, which is when I'm going into a junction, the currents have to balance essentially, right? So I'm going to say that current 1, I'm going to look at this junction right here. Okay, I could look at the other one. It doesn't really matter. I'm going to look at this junction right here. So going into this junction, current 1 is going in. So I go I1. Okay, now I'm going to say that needs to be equal to the currents coming out. So what's coming out? Well, I got I2 coming out here, and I got I3 coming out this side. So that will be equal to I2 plus I3. And that's Kirchhoff's first law. It's just that whatever's coming in has to equal what's coming out. Now I know what's going in and what's going out because I've already labeled the directions of my currents. Now remember, if I label them differently early, that's fine. I just need to make sure that I'm being careful, being consistent. The numbers will come out in the end. If you get a negative current, just recognize that means that you put the wrong direction on your current. Now, if the currents are labeled for you and you get a negative current, that's a problem. Okay, but if you choose a direction, all that means is that you chose the wrong direction. All right, let's say, okay, so I've got 2 equations now. I need another one. Now, you may say, oh, well, Kirchhoff's first law was so much easier. Let's just use that one. But you'll notice that if I do that, I've got 2 and 3 in and 1 out, which is going to give me exactly the same equation. That doesn't count. They have to be different equations. So I'm going to have to do one more of Kirchhoff's second law. I've got some other options. I could do the full loop again, but this time go through the 9 ohm resistor. I'm actually not going to do that. I'm going to just do the small loop here because I want to show you how that works. So I'm going to go through this loop right here. Okay, so any loop is fine as long as I start and then end at the same place. So I'm going to start right here on the other side of the 6 ohm resistor, and I'm now going to go through this. All right, so I'm going through the 6 ohm resistor. Note that I'm going in the direction of the current, so I'm going to lose some potential there. So how much potential am I going to lose? Well, it's going to be negative 6I3. Okay, so I'm going to follow around the circuit. So I go through there, follow, go around the circuit. Now I'm going through this resistor, but notice I'm going against the current. That means if I go with the current this way, I should be losing potential. I'm going against the current, which means when I cross through this resistor, I'm actually gaining potential, right? So the potential that I gain there is 9I2. So that's going to be a positive 9 I2. Okay, and then if I follow it around, I get back to where I started. Now, this really isn't anything special, right? We already knew, because this is a parallel circuit, that the potential here has to be equal to the potential there, right? This is nothing new. It's not anything special or different from what we've already done. It's just an application of that, right? We already knew that the potential here and the potential there have to add up to 3 volts because that's the total potential lost. Those things we already know. This is just a way of putting it together. This is also a way to be able to deal with more complex circuits, like I said before, that may have 2 or 3 batteries. It may have several different resistances. It may have variable resistors, any number of things that could make things a little more interesting. Interesting, of course, in this problem. So from here, I should be able to take those 3 equations, and this would be on a paper 2 or a paper 3 or something like that, probably paper 2, which means that you could then use your calculator with a linear equation solver to solve this problem, okay? So if you can go ahead and do that, I'm going to write the answers right here. So of course, what you should get is the same thing that we got last time we did this problem, which is that I1 is 5 over 11, I2 is 2 over 11, and I3 is 3 over 11. You can check those in any of these equations and it should work out. Note that if you did decimals, that 5 over 11 would be 0.45454545, and so since we have 2 sig figs, it would be 0.45. 2 over 11 would be 0.18181818, so 0.18 would be appropriate, and then 3 over 11 would be 0.272727, so 0.27 would be appropriate for that. All right, so that's it. That's Kirchhoff's laws. Just go through the same process that we did. Choose a loop. As you're going through the loop, add positive. Anything that's going to gain potential, you add. Anywhere where you lose potential, just follow all the way around and you can create your equation just like we did. For Kirchhoff's first law, choose an intersection, put the in on one side, put the out on the other side, add them together. It should be fairly simple, fairly straightforward to set up. Once everything's set up, like I say, you should be able to just put this into your calculator, do the lin solve, to solve the system of linear equations, and it should be able to give you the numbers pretty quickly at that point. Of course, you're always welcome to solve 3 variables by hand, but I'm not going to do that. I'm too lazy. Anyway, that's it. That's it for Kirchhoff's laws for circuits. Good luck as you start with your homework.